So in this video, I'm going to do a few temperature conversions. I'm going to be going from Celsius to Kelvin in these ones here. So Kelvin is 273.15 plus whatever temperature you have in Celsius. For the purposes of what we're going to do, don't worry so much about that 0.15, just do 273. So 273 plus 0 is going to work out to be, of course, 273. So that is going to be my temperature in Kelvin. Now let's try that with 25 degrees Celsius. So 273 plus 25 works out to be 298 Kelvin. That's how I go from Celsius to Kelvin. To go from Kelvin to Celsius, just subtract 273 and you're going to find your new temperature. All right, so I'm going to be doing a few conversion problems here. I've got P1, V1, and T1, and P2, V2, and T2. I'm going to be looking to see how the combined gas law will tell us. Now, this first one here, I'm going to be looking at the temperature being constant. If the temperature is going to be constant, that means it's not going to change. For our purposes, with the combined gas law, just put a 1 then for the first and the second temperature and kind of cancels them out. I start with 150 mils for volume. My initial pressure going to be 0.947 atmospheres. And the question is, what is the volume going to be? So my second pressure, what I'm going to be going to is 0.987 atmospheres. So I'm going to use the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Now I'm just going to be filling those in with my numbers. So P1, 0.947, V1, 150, T1, 1. Remember, that just kind of cancels it out there. P2 is going to be 0.987. My volume is going to be my unknown, so I'm going to put X, and that all goes over 1. Now, multiply these, then divide by 0.987. X is going to work out to be 143.9 mLs. So that's how the combined gas law will give me my new volume. All right, going to just do the same thing again. P1, V1, and T1, P2, V2, and T2. Set that up first. Now let's take a look at my question. So the balloon is filled with helium gas, floats up from 1 atmosphere all the way to 6.5 kilometers, where the pressure is 0.5 atmospheres. What volume will the balloon be? So temperature is not going to change, so I'm going to put a 1 there since there's not going to be a change, and this way it's going to kind of cancel them out. I don't really need to factor them into this. My initial volume, 500 mLs. My initial pressure, 1 atmospheres. The question is, what is going to be my new volume when the pressure is 0.5 atmospheres? So my second volume is going to be the unknown. P1 V1 over T1 equals P2 V2 over T2. I'm going to fill those in with my numbers now. X, in this case, is going to solve out to be 1,000 mLs. So the volume goes from 500 mLs to 1,000 mLs. That balloon might pop. All right. Here I have a balloon filled with oxygen gas 150 feet underwater where the water pressure is very high. Fill it to 15 liters and you release it where it's going to float up. Pressure at the surface is only 1 atmosphere. What's the balloon's new volume going to be? Spoiler alert, this is going to pop before it reaches the surface. This is why people escaping a submarine, you don't want to hold your breath. Why? Your lungs will literally explode. So, don't do that, kids. So P1 V1 T1, P2 V2 over T2. In this case here, it doesn't say anything about the temperature, so we're going to assume that there's going to be no change. So just put a 1 there in place of that. So I start at 4.4 atmospheres, and I fill it up to 15 liters. Now my new pressure is going to be only 1 atmosphere. What is the new volume going to be? So I'm going to use my equation here, fill in my different numbers for P1 and V1 and P2 and V2. That is going to work out to be X equals 66 liters. That balloon would have popped. Don't hold your breath from escaping from a submarine. It's just not a good idea. All right, now I'm going to be trying a slightly different version. This is Charles' law where pressure is not taken into account, but we still write out everything as before, P1, V1, and T1. So pressure is remaining constant, so I'm going to put 1 for both before and after. So first thing I need to do when I have temperatures, convert those into Kelvin. Add 273 to each one of those. So 50 degrees Celsius becomes 323 Kelvin. 25 becomes 298 Kelvin. So I can fill those in. My volume is 752 mLs at the start. What's the new volume? That's the question. I started at 298 Kelvin, it's 25 Celsius, and I end at 323 Kelvin. That, of course, is going to be 50 degrees Celsius. Fill in my combined gas law. I'm going to use 1 for the pressure to sort of cancel those out. And I'm left with this equation here. Best way to do this is to cross multiply and divide. In this case, that's going to work out to be 2.52 equals X over 323. Solving that out for there, X is going to equal 815 mLs. So with that change there, my volume increased. So set this up, cross multiply, and divide to figure out your correct answer. Keep it as mLs because that's what I started with. All right, sample of nitrogen gas is in a piston with a freely moving cylinder. A freely moving cylinder means that the pressure will always be the same because the cylinder will move. First thing I'm going to do is I'm going to write out and convert things into Kelvin. 0 Celsius, 273 Kelvin. The question is, what is the new temperature? So that's my unknown. My initial is 273 Kelvin. Pressure is constant, put a 1 there. I start with 375 mLs. My second volume is going to be 500 mLs, which is going to be half a liter. Now I can set that into my combined gas law. Fill in the different numbers, cross multiply and divide, solving for x. In this case, x is going to equal to 364 Kelvin. So that temperature went up drastically as a result of the change. That works out to be 91 Celsius, almost boiling point of water. Pretty hot. All right, here I have another sample of hydrogen gas. What is the volume going to be when I increase the temperature? So start at 27 Celsius, 300 Kelvin, convert that to a new temperature, 373 Kelvin. So I'm going from 27 Celsius to 100 Celsius to boiling. My initial volume, 1.55 liters. My second volume is going to be the unknown. Set up my combined gas law, fill in, cross multiply and divide. X is going to work out to be 1.93. So I started with liters. My ending unit is also going to be liters. This one, another one with the volume not going to change, so kind of different than what we've seen there. Convert my temperatures from Celsius to Kelvin. Now, here's my initial temperature, ending temperature, initial pressure. My unknown pressure is going to be the second one. Fill in 1 for my volume because that's not going to change. That can kind of cancel out. So fill in the combined gas law, cross multiply and divide. X is going to work out to be 3.3 atmospheres. Another one here, constant volume. Change the temperatures, 298 Kelvin, 77 Kelvin, very cold. Fill in my initial pressure, 2.7 atmospheres, my initial temperature, 298 Kelvin, dropping all the way down to 77 Kelvin. Volume is not going to change because it doesn't say anything about that. Cross multiply and divide, solving for x. X is going to work out to be 0.698, and I started with atmospheres, so this is also going to be atmospheres. It's going to drop quite a bit in this pop can here due to the drop in temperature. Another one here, constant volume. Convert my temperatures from Celsius to Kelvin. Have to do everything there so that nothing is divided by 0. So 1 atmosphere of pressure is what I start with. 298 Kelvin is going to be my initial temperature. My final temperature, 373 Kelvin. My pressure is going to be unknown at the end. Now, it says it's a 2-liter bottle, and you might be tempted to fill that in. However, I'm going to stay in that 2-liter bottle, so even though it's 2, I can kind of cancel those out because they're going to be on either side the exact same. It's going to work out to be 1. It'll just simplify to do it this way. Fill in my data, cross multiply and divide. I'm going to solve for x, and I'm going to get 1.25, same unit I start with, so I'm going from atmospheres. Sadly, there will not be any explosion. The 2-liter won't fail until 10 atmospheres. I'm going to have to heat it up way more. Don't try that at home, kids, but no explosion with this one. All right, helium-filled balloon being risen up to the level of Mount Everest, where the temperature and air pressure is going to change. So now I have everything that's going to be coming into play. This is why it's called the combined gas law. All of those things are going to be combined here. Like before, need to convert all my temperatures from Celsius to Kelvin. So 25 becomes 298, negative 10 becomes 263. My new volume is going to be my unknown. I started with 50. Don't know what I'm going to end up with there. That's what I'll solve for. I start at 298 Kelvin in 1 atmosphere. I'm going to be ending at 263 Kelvin in 0.33 atmospheres. Solving that out here, cross multiply and divide. Solving that out, 133.72 liters. So that balloon has drastically increased in volume, way bigger than it used to be. All right, have another one here. It's a sealed container, and I'm going to see how things are going to change when I put stuff in a different temperature water. So convert Celsius to Kelvin, going from 303 to 274 Kelvin. Here's my initial pressure, initial volume. There's my second volume. The question is, what is going to be the new pressure? Set it up before. Everything works in this combined gas law. Solve for x. X is going to work out to be 1.66 atmospheres. So with all that said, it didn't increase the pressure that much, but it did increase it. Combined gas law tells you how. All right, 17-liter gas sample at standard temperature and pressure. Remember, that's going to be 1 atmosphere and 0 degrees Celsius. That works out to 273 Kelvin. So there's my initial temperature. Here's my initial pressure. And I'm starting with 17 liters. I'm going down to 10 liters. So at 5 atmospheres, what's going to be the new temperature there? So setting that all up, solving for x, x is going to work out to be 802 Kelvin. So I drastically increased the temperature of that by increasing the pressure and decreasing the volume. You can solve that all out with the combined gas law using all the different parts of all the different equations.